My name is Regan Zite, and I'm a senior undergraduate student in the Department of Physics at the University of Washington. I've been working with the Helium-6 CREST project at the Center for Experimental Nuclear Physics and Astrophysics. Today, I will be presenting my research on a monitor detector for relative normalization. We'll quickly go over what the Helium-6 CREST project is and why the detector I'm working on is important to the project. We'll talk about the system that I'm using to test the detector, the results that we've obtained so far, and what the next steps are moving forward. The Helium-6 experiment seeks to measure the energy spectrum of electrons emitted in beta decay, and we do this using cyclotron radiation emission spectroscopy, or CREST, which was developed by the Project 8 collaboration. In this experiment, gaseous helium-6 decays in a mostly uniform magnetic field. As the beta particles are emitted in decay, they are trapped using a series of coils and enter a cyclotron motion with a frequency that's inversely proportional to their energy. By measuring this frequency, we are able to construct the entire beta spectrum. From the spectrum, we'll pull the Fears coefficient. According to the standard model, the Fears coefficient should be 0, so any variation from this will be indicative of physics beyond the standard model. This apparatus takes measurements in a finite bandwidth between 18 and 24 gigahertz, which only covers a small portion of the energy spectrum. By tuning the magnetic field strength from 1 Tesla to 5 Tesla, we will be able to construct the entire beta spectrum. An important part of this experiment will be to piece together each portion of data taken. We will do this using a detector for relative normalization. This detector will sit here at the entrance of the helium-6 gas to the CREST apparatus, and this will act as a monitor for how much helium-6 is entering the system at any given moment. It is important that this detector have stability on the order of 10 to the minus 4. This is the current system we're using to test a photodiode pin detector. On the left, you can see a cube-shaped vacuum chamber. The detector itself sits on the top flange, and through this axis, there is a slide holder, which holds a radioactive source for calibration. All electronics are connected to true ground via an isolation transformer, and all motors move through a separate ground. The photodiode pin detector sits on a Peltier device, which is connected to a proportional integral derivative controller. This allows us to control and monitor the temperature of the system. The detector itself is cooled using the PC water pump seen in this photo. With this system, we are able to get the detector to a minimum temperature of -8 degrees Celsius. Our first run was done using an Americium-241 alpha source, with the detector cooled to -8 degrees Celsius. We will analyze this data using a logarithmic Allen deviation plot. This allows us to see how our system varies over time. As can be seen here, we do have stability on the order of 10 to the minus 4 for the alpha source. The data that I've shown you today was taken in December of last year, so our first step will be to repeat these measurements to ensure nothing has changed in the system. If that is the case, moving forward, we'll replace the Americium-241 source with a Strontium-90 source. Strontium-90 is a beta source, and its spectrum is more closely related to that of helium-6. This will allow us to more closely monitor any gain drifts in the system and ensure that our stability is, in fact, low enough to meet the needs of the experiment. Thank you so much for listening. I look forward to seeing you and hearing your questions at the poster presentation.